Data Flows Masterclass on machine learning and speech. My name is Rob van Eyck. I'm the Managing Director for Future Privacy in Europe. And I'll be hosting this masterclass today alongside my colleagues, Dr. Sarah Jordan and Brenda Lyon. Let me first quickly highlight the Future Privacy Forum as a non-profit organization that serves as a catalyst for privacy leadership and scholarship, advancing principal data practices and supporting and emerging technologies. And we try to bring together industry, academics, consumer advocates and thought leaders to explore the challenges posed by technical innovation and develop privacy protections, ethical norms and workable business practices. So the Digital Data Flows Masterclass series began as an 8-part program hosted by Future Privacy Forum and the Brussels Privacy Hub, which is an academic research center at the Free University of Brussels. And you can see the list of our previous classes here, and all of the video, so the slides and the other materials are available at fpf.org/classes. The goal of these classes is to provide technical basic subjects that are of the greatest interest to lawmakers, but also public policy experts, and specifically those technical topics that have implications for privacy and data protection. So in other words, we don't spend much time on what the law is or what the law should be. Our goal is to teach the technical and conceptual basics of what policymakers might need or what to know in order to consider the best legal and policy solutions. So today's topic is machine learning and speech, which covers both supervised and unsupervised learning. Big questions like how do voice-based digital assistants learn to communicate with humans, but also machine learning as it is at the heart of how digital assistants learn to understand human language and improve conversational communication. Digital assistants are trained on data sets of audio and video recordings that differ in size, labeling, diversity, and other characteristics. It is a more advanced masterclass. It builds upon the first masterclass in this series, listed in the top of the overview on the right-hand side of the slide, which was on artificial intelligence and machine learning. So with that, one note on housekeeping. Today's session is being recorded and we will be tracking questions and answers in the Q&A function. And there will be the Q&A function, in the Q&A session after each presentation. We have 2 speakers lined up. I'll do a quick introduction of Prem Natarajan, who is the VP of Alexa AI in NU, which will join us in the second half of this webinar. And Brenda, I leave the introduction of Professor Maureen Capua to you.
I think I'll leave that to Sarah.
I'm sorry.
Great. Good morning, and thank you for joining this masterclass on machine learning and speech. It's really a pleasure to have all of you joining us this morning. I am thrilled that we have Professor Maureen Capua from University of Maryland joining us today. Maureen is an associate professor in computer science at University of Maryland with a joint appointment at the University of Maryland Institute for Advanced Computer Studies. And she's a member of the CLIP Laboratory, Computational Linguistics and Information Processing Lab, where her research focuses on multilingual natural language processing and machine translation. Maureen is the recipient of an NSF Career Award, research awards from Google and Amazon, as well as Best Paper Awards from the SEM and Talon conferences, as well as Outstanding Teaching Awards at University of Maryland. Beyond her amazing bio, Maureen has papers of interest on an archive that I'm sure many of you who are interested in translation performance will find of keen interest. If you found her work on neural machine translation, I'm sure that you're going to be in for a treat that helps you to understand some of this advanced work on bidirectional translation, as well as other challenges associated with text complexity and neural machine translation. Before we shift to our expert, Professor Maureen Capua, if everyone can hold your questions for her until the end and place those in the Q&A function, we'll make sure that we get all of your questions addressed. So without further ado, it is my great pleasure to turn the floor over to Professor Capua.
Thank you, Sarah. Let me share my screen. Can you see my slides okay?
Yes.
Okay, great. Good morning, everyone. I'm excited to be here this morning to tell you a little bit about how we use machine learning these days to build models that understand languages, multiple languages, and translate them automatically. The goal of my research is to enable communication across language barriers. And that's a challenging task because there are many languages in the world. More than 7,000 languages are recorded today, according to Ethnologue. Many of these languages are spoken by few people, and 43% of these are considered to be endangered. So communicating and accessing information across all these languages is a very daunting task. And with my research, I'm aiming to make this a little bit easier by developing technologies that can help us break language barriers. So the key application that we use to do that is, of course, machine translation. You might have used Google Translate, Microsoft Translator, or other online tools to automatically translate between languages. Here, I'm showing you what a research system can do. This is a system that was built by one of my PhD students 2 years ago for a machine translation benchmark between Chinese and English. So we have a Chinese sentence that you might or might not be able to read, and you have here the output of our system in English, which I'll read briefly. So it says the Chinese capital, with its surprisingly high-speed internet, sophisticated technology such as face recognition software, has invested heavily in artificial intelligence and has unrivaled international energy and is one of the most exciting cities for exploration-minded foreigners. So it's not perfect, right? It's a bit of a run-on sentence, but you can get, it makes sense, and it actually conveys the meaning of the Chinese pretty accurately. You can quibble on some of the word choices, but the core meaning is there and it's understandable. And that is much, much, much better than the kinds of output we were getting with systems even 5 years ago or 10 years ago, where we would just have like word salad on the output side. So we've seen a lot of progress in machine translation in the past 5 years. And I want to give you a little bit of an insight into how that's possible. So what makes this kind of translation tools work is viewing the task of translation as a machine learning problem. And we do that by viewing the task of translation as if I'm given an input sentence in English, I find the French translation by finding the French sentence that has the highest probability given the input English sentence according to some probabilistic model with some parameters that I'm denoting here as theta. There's a learning task, and learning here means finding good values for the parameters that parameterize this probability distribution. So we want to find good values for these thetas. That by good, I mean values that give high probabilities to translations that have been produced by humans. And so doing that requires a lot of data, including text that's been already translated by humans, for instance, from international organizations like the UN, the EU, that translate a lot of text as part of their normal operations. So we can leverage that to build good models. And I'll talk a bit more about the different learning paradigms that let us do that. What I want to say for now is that this is a pretty old formulation. Since the early 90s, this is how we've thought of translation as machine learning. We've seen a lot of progress in the past 5 years by modeling this probability distribution using deep learning, using a giant neural network that is used to capture the relationship between our French sentence and our English sentence here. So this picture here gives a glimpse of how this complicated neural network works. So here, if I'm trying to translate an English sentence, economic growth has slowed down in recent years into French. I'm going to do that by first encoding the English sentence into some vector representations. I'm going to read the English sentence one word at a time, create a representation for each word within its context, and use that information to generate the French translation one word at a time from left to right. So I'm going to generate the first word based on what I know of the English, and then generate the next words based on the French words I've previously generated, and of course the input English sentence. So that's what the equation at the bottom captures. We're generating our French sentence one word at a time, condition on the previous French words generated and the English sentence representation. The progress here comes from the fact that we're able to represent this probability function with a single giant network, while previous model broke down the translation process into independent decisions, translating words one at a time, then figuring out how to arrange them in a correct form in the output language. By being able to do all of these decisions at the same time and training the single models to learn how to do all these decisions jointly, we're able to have models that reach translation quality that is much better than before. However, that's not translation as deep learning is not a solved problem. It's a very challenging task. Even with this deep learning formulation, in order to train these large networks that have millions of parameters, we need a lot of data. We need millions of translation examples to do a good job at translation. And that's a problem because, you know, maybe we can get millions of translation examples between French and English or English and Chinese, but we don't have this amount of data for many other world languages. And so we do a much worse job for these other languages. This formulation of translation as deep learning also raises fundamental challenges in machine learning. We are dealing here with a use case that is in some ways a little bit different than the standard machine learning tasks, where maybe you're trying to build a classifier that distinguishes between a small number of options. Here, the output space is very large, right? It's the space of all possible sentences in the language. So exploring that space efficiently is a challenge. Even at the word level, if I'm just trying to predict the next word, well, my options are all the words in French or all the words in English. So that's a very large space, and we have to be smart about dealing with that effectively. Another challenge is that there's always more than one correct output. It's not like, I'm making a binary decision and there's a right answer and a wrong answer. There's not a single correct translation for a given input. If you give it to different professional human translators, same text, you're likely to have different translations, right? And so that's challenging here because to train our systems, to do a good job of learning parameters for our models, we need to have a signal of when we're right and when we're wrong. But there are many ways to be right and many ways to be wrong. And so that's a challenge. Finally, now that we have systems that work well, they're deployed in the real world. And so when they make errors, these errors have real world impact. And that's, of course, an important problem. But the models we're dealing with are very opaque, right? They're these giant neural networks that I just showed on the previous slide. So we have lots of parameters, but we don't really, it's hard to figure out when something goes wrong to pinpoint exactly what went wrong where. And so that's definitely a challenge in deployment. Also, our models are developed most of the time in the lab on some standard test sets, data sets that are designed, that are kind of independent of use cases. So we can measure translation quality in the lab, but that doesn't really tell us what the impact is going to be. So that's definitely something that is an area of active research. So what I want to do today is tell you a little bit about how the field at my lab are looking at some of these challenges, focusing on learning from diverse types of data to do a good job for many other world languages, and thinking a little bit about how we can make systems a bit more responsive to user needs. But before I do that, I'd like to point out that even though I'm talking about translation today, the models that we're using to translate are general purpose tools to process and generate natural language. So they're usually called sequence to sequence models because they take a sequence of words as input and output a sequence of words. In the case of translation, this input sequence is a sentence in French or in any language, and in the output is a sentence in another language. But you can use the exact same technology to do lots of other tasks. For instance, building dialogue systems that might take an utterance as input and then generate a response as the output sequence. You might use the same models to perform text summarization, where you might have a document as input, which is a much longer sequence, and then output a summary of that document. Systems that learn to answer questions, that transfer style, maybe have a complex text as input and then generate this equivalent version that is simpler. All of these can be framed as sequence-to-sequence transfer and can be addressed under the hood with the similar deep learning models as the models I'm talking about today for translation. The models I'm talking about here also share their architecture with models that just learn how to model a sequence, language models, right? That don't necessarily try to transduce an input sequence into an output sequence, but just model a sequence. I want to model English, so I'm going to model how English words are organized. And they also, the same architectures are also used to learn word representations, word embeddings that capture the meaning of a word by looking at what context it's used in. So I'm going to focus on translation, but everything I'm talking about is relevant to pretty much any use of machine learning for processing and analyzing natural language. So the first question I'd like to focus on is how can we train these large neural models with limited translation data? We're always going to have to deal with, we never have as much data as we'd like. I already mentioned that there are disparities across languages. English and French have a lot of data. Swahili has a lot less data. But even for French and English, we want to train our models on language that is as close as possible to the situations they might be applied to later, right? So if I want to translate legal text, I'd like to train on as much legal text as I can. But there's always limitation in the data that has been translated before. In particular, it tends to be more formal data. It comes from international organizations or from news. And so if I'm trying to translate, for instance, tweets, I'm not going to have a lot of translated tweets to learn from. So no matter what situation I'm in, I kind of never have enough data. So what can we do about that? The way we're dealing with this is that we have a range of learning paradigms that we can draw from to exploit diverse data sources. The typical setup is supervised learning, where we're going to learn from examples of translations. And at the other end of the spectrum, we have unsupervised learning, where we're learning just from examples of texts, say in French and in English, but that are not paired. I just have some French news and some English news, and I'm going to try to learn how to translate from these separate outputs, separate texts. So usually the way I explain the difference between supervised learning and unsupervised learning to my students in a machine learning class is that I say supervised learning is like you're learning, your goal is to learn how to take a test, and you're learning by being given lots of examples of previous tests, previous exams with the answer keys. So it's supervised because you're given examples of answers. But in unsupervised learning, you don't have you'd never given the answer keys. You might have lots of reading materials on the topic. You might have examples of previous tests, but without the answer keys. And you have, from this information, you have to learn something useful so that when you're given the test, you can do a good job. And so that's what we're doing here with our translation systems. In supervised learning, we're giving examples of translations that the models have to learn from. And in unsupervised learning, we're just giving examples of texts in the languages of interest. There's no example of the connection between the two that the model can directly try to capture. So to be a little bit more precise, in supervised learning, we are going to learn from these pairs of input sequence, output sequence, so translations here, right? And we are going to use these to guide our model to give high probability to this correct translation. So I have an English sentence, a French sentence. I want to find parameters for my model that give high probability to the French sentence given the English sentence. That's a traditional training framework. By contrast, in unsupervised learning, sorry, I need to make sure my slides are everything in sync. Okay. By contrast, in unsupervised learning, what can we do? We just have English text and French text. So what we can do is learn what we call a language model for each language. A language model is a probabilistic model that predicts the next word given the previous words in a sentence. So that's something that's easy to do given running text, right? And it's very simple in a way, but it's very powerful. So if I have some French data, I can use it to find parameters of the model that assign good probabilities to the high probability to the next word I observe in the text, given the previous words. I can do that in French. I can do that in English. So this might seem kind of simplistic, compared to the more complex task of translation. But this task is very powerful when we learn these language models from lots of data. And that's typically what we're going to do. We're going to learn this from millions of sentences. And what we learn is the patterns of language use, right? And there's a lot we can learn from, for instance, knowing similar words that have similar meanings are going to occur in similar contexts. And so these models are going to be able to capture that and are going to be able to figure out, that which words that are similar in meanings because they occur in similar contexts. They're also going to be able to learn something that is a little bit like syntactic structure, because by looking at what words occur next to what words, we can figure out what are patterns that lead to well-formed sentences in French or in English. So despite the idea that we're just predicting next word given previous words, we can learn a lot that is very useful here. So how is that useful for translation? Well, if we look at the big deep learning model that I talked about earlier, we have a network that encodes an English sentence at the bottom, and then a network that generates a French sentence at the top. Right? And we can think of each of these as, we can think of the bottom one as an English language model, and at the top one as a French language model. So if we have models that know how to represent these two languages independently, we can use them to kind of initialize the bottom part of the network and the top part of the network. And we're already in a better place to start building a translation model than if we're starting from scratch. We're still missing a connection between the English and the French, of course, here, right? And that's going to be needed to do a good job at translation. And so in full unsupervised learning, we can use word level dictionaries. Sometimes some of them are either taken from existing resources or learned automatically from data to try to capture cross-lingual correspondences. There's interesting work that does this, but it's still at the proof of concept stage. It kind of doesn't work in realistic scenarios yet. What people do in real systems, in deployed systems, is a middle ground approach, semi-supervised learning, that combines data, a little bit of paired data, a little bit of translation, supervised data, and then a lot of monolingual text, unpaired, unsupervised samples. This is a much more realistic scenario because usually when we're building a system for a task we care about, we always have a little bit of data, maybe not millions, but we can typically get or order translations for thousands of sentences. So it's rare that we're in the fully unsupervised scenario. Usually we have a little bit of supervision and we're trying to figure out how to do better with unsupervised unpaired data. So how can we do that in the context of translation? One common approach is pretty simple, and it's called back translation. What we do is we take the limited translation data that we have to build a machine translation system, and we use it to translate the monolingual data, maybe in French. So we have some paired data. We have some monolingual French data for which we don't have an English translation, and we just use our translation system to generate an automatic translation. It might contain some errors, but that's better than nothing. And we treat that as a new training example. We concatenate the original translation data with the machine translated data and use all of that to build a new system. This works pretty well. And it has the advantage of being quite simple and is a technique that is used in pretty much all machine translation systems today. Another approach that is a little bit more involved, but I think makes a lot of sense intuitively, is called reconstruction. In this approach, when we have a sentence in one language, this is taken from a Swahili data set, I think, and we don't have a translation for it, we can still use it to improve our systems by translating it first into the other language, so here English, And then what we can do is translate the English back into the original language. So we are able to compare the reconstructed sentence with the original. And if the two are similar, this is a good signal that the English translation was good. If they're very far apart, we probably have a very bad English translation, and then we should probably not use it as evidence to learn better parameters for our system. So this is also a technique that's used to incorporate monolingual data in training machine translation systems. It's a little bit more involved than the one I was just describing earlier, because now we have to have 2 additional machine translation systems that increases the training costs here, and incorporating the similarity in the training process is a little bit more complicated. But there are ways to do that efficiently. One of my PhD students, Sheng Liu, came up with a model that learns how to translate between the 2 languages at the same time. So instead of going from English to French or French to English, he has a model that can do both. So that simplifies this process a little bit. And then there are ways of incorporating the similarity into the deep learning models that, that make training reasonably easy. I'm also talking about this reconstruction framework because even if we don't use it explicitly to train system, it's a very useful framework to think about semi-supervised learning in general. We have a recent paper with my student Weijia Xu that shows that we can think of reconstruction as a general framework and think of a lot of semi-supervised learning techniques as special cases of reconstruction. And so that provides a good framework for analysis. So for instance, the back translation technique I was talking about in the previous slide, you can think of it as just doing half of the reconstruction process. And then we have analysis that shows that even though it's doing only half of the process, it's a very good approximation of an ideal reconstruction scenario. So I won't dive too deep into that, but I'll include references to the papers for anyone who's interested. Okay, so the main takeaway here is that these techniques, these semi-supervised learning techniques, are key to the recent successes of machine translation. All of the big tech companies that have online translation services, Google, Microsoft, have been pushing really hard in the past 5 years with improving the translation quality of their systems. They've claimed approaching human level accuracy. It's not clear what this means. It depends on the circumstances and the kind of text that's being translated, but there's no doubt that the translation quality is really good and much better than it was before. And all of these systems use under the hood a combination of the learning techniques I talked about today, learning from supervised settings with examples of translations, and in semi-supervised settings with monolingual data where we somehow generate automatically a translation when it's not given to us because it's been translated by a human before. So all this is great, but at the same time, it's still not a solved problem despite all these successes. We still need better learning algorithms to really scale to all of the world's languages that I was talking about at the beginning. There are issues not just to learn from very small amounts of data, but also to adapt to all of the domains of interest, all the varieties of language. When I say English, it's not a uniform formal language. There are many varieties of language within English. And I'm just talking about text, but when we move to speech, there are all sorts of issues that arise with differences in accents and so on. So, semi-supervised and supervised learning techniques I talked about enable to get really good translation, but not a solved problem. So now I'd like to talk a little bit about, now that we have models that can be trained and that can do a good job, at least some of the time, how can we make them more responsive to user needs when we deploy them? Models, no matter how good they are, always fail, right? And sometimes catastrophically. A particularly famous example, infamous example, came out 2 years ago when there was an incorrect translation of a Facebook post that led to the arrest of the man who had made the post. So the post was originally in Palestinian Arabic, and it was just saying good morning. And the Facebook translation system translated it as attack them, which obviously was incorrect, but someone read it, and that led to the arrest of the man on the basis on the machine translation. It's only when someone who could read the original and understand the original realized that this was not at all what he was saying, that the man was released. So this raises a lot of issues. I mean, there's of course a technical issue of why was the translation wrong, but there are also issues that arise with the trust that people have in systems, and how can we present output so that people understand in what way systems might fail. So that's a big question, but for now, I just want to try to focus on, as researchers, what can we do to try to detect when such bad translations happen. So I'm going to focus on what I'm calling fluently inadequate translations, which is one type of the catastrophic failure. So I'll argue that the Facebook example I was just talking about is a case of fluently inadequate translation. And here, what we're using is the two typical dimensions of quality that I use to evaluate machine translation system: adequacy. So an adequate translation is a translation that accurately conveys the meaning of the source. And the other dimension is fluency. A fluent translation is one that's well-formed in the output language. So here are examples of translation that span the spectrum of fluency and adequacy. So we have in green short sentence phrase in Turkish, and we have the output by different machine translation systems. The first one, he was covered in blood, is both adequate and fluent, so it conveys the meaning of the source accurately, and it's a well-formed English sentence. There was blood on is disfluent, and also but adequate, like the meaning is roughly correct. The one at the bottom right corner in the Kandlar is just completely wrong. It's not well-formed in English, and it has nothing to do with the meaning of the source. But the one we're focusing on is the one highlighted in red here, drinking blood, which is problematic because it's pretty much well-formed in English, even if it's not a full sentence. But the meaning is wrong. There's no meaning that has to do with drinking in the input, yet the system produces that. And so if someone looks at the output, they don't know how to read Turkish, they have no way of knowing it's wrong. So we'd like to detect these fluently inadequate translation, right? Ideally automatically, so that we can embed such a detector in a system and maybe warn users when such fluently inadequate translations occur. We're also interested in figuring out how often, how frequent they are, and in which situations do they occur, for what type of systems are they most frequent. So we came up with different metrics to try to detect these errors automatically. And these metrics are based on separately quantifying fluency to discriminate fluent from disfluent translation, and then adequacy to separate adequate from inadequate translation. So to quantify fluency, we're going to use a language model, like the kind of language model I was talking about earlier, these models that predict the next word given the previous words. If we have the probability of a sentence according to a language model, we can assume that fluent sentences are going to have higher probability than disfluent sentences. We tweak this score a little bit to not penalize longer sentences and to account for outliers. But at the core, the score we're using is just the language model probability. And we evaluated a language model on its ability to classify separate fluent and disfluent sentences. It's not perfect, but it's doing a good enough job for our purposes. Then we turn to building an adequacy, a model to quantify adequacy to tell us whether, given an output, it's correct or not. So here we worked, the approach we took consisted of computing the similarity in meaning between the machine translation output and a translation that was provided by a human. So that's not something we can deploy when we don't already have a human translation, but that's the first step. And we came up with lots of different ways of doing that. I'll just give you a quick sense of two of them. The first one that is named BLEU after a commonly used machine translation evaluation metric counts matches, exact matches between words and short sequences of words between the system output and the human translation. So that's what we're calling n-gram matches. So we have to produce an exact match, the exact same word, exact same form to get credit for it. And the other one that goes by this acronym BVSS computes similarity, semantic similarity for all the words in the human translation and the machine translation. We do that using representations derived from a neural language model and combine them to get a sentence level score. So, both of these metrics have problems. The first one only accounts for exact matches. The second one doesn't know much about the structure of the sentence, just takes a sentence and treats it as a bag of words. But in combination, they do pretty well. On synthetic data, we find that they do a really good job at separating adequate from inadequate translation. So we're going to use these metrics, these adequacy and fluency metrics, to detect fluently inadequate translation. And we're going to do that on a large number of systems. We considered 36 machine translation systems that we built that cover 6 language pairs, so translating from Arabic, Chinese, Farsi, German, Korean, Russian into English. We looked at 3 different training configurations where, we were translating TED Talks there. So that's the domain of interest. And we compared models that were trained on kind of general English, large amounts of general English, but maybe no TED Talks. Model that were only trained on TED Talks. So that have a really good, the data is a really good match for the domain of interest, but there's not a lot of it. And then models that combine both, that's what we're calling the adapted models. And we also looked at 2 different machine translation paradigms, the neural model that I've been talking about, and then the older statistical machine translation model. So the table at the bottom just shows a BLEU score, so the translation quality for all of these models. And there are a lot of numbers, but what I want you to get from this is that there's a wide range of translation quality there. And the neural models tend to have higher translation quality than the older statistical models. All right, so we detected the fluently inadequate translation output of all of these systems. And so here's what we get. Here we have 1 dot per system in neural systems in blue, statistical systems, older systems in green. The x-axis is the BLEU score, so increasing translation quality from left to right. And then percentage of fluently inadequate output on the y-axis. So we see that for the same quality, neural models have more fluently inadequate outputs than older models. And if we just look at the blue dots, we see that the percentage of fluently inadequate outputs improves rapidly as the BLEU score improves, when the model gets better. So that's good. If we break that down per language, we see that the neural models have consistently higher percent fluently inadequate than the statistical model for all languages. And the gap is particularly large for Korean, Russian, and Chinese, where our models are doing worse than for Arabic and German, for instance. We see that the adapted models, the one that use both general data and TED data, do better. And we see a larger improvement from adapting to the domain of interest for neural models, which is great. Finally, I should note that on the y-axis, even the highest percent of fluently inadequate is small, right? It's under 2% here. So I don't want to focus on the absolute number too much because there's a bit of noise in the method we're using to detect the models. But still, we can confidently say that these are kind of rare examples. So to sum up, our study showed that the fluently inadequate translations are infrequent, but I argue that they're still very important errors to look at because they're likely to mislead users because they look plausible, they look fluent, but they don't convey the meaning adequately. So that's a problem. And even if they're rare, there's still a problem because there are millions of translation requests per day in a system like Google Translate. So even if I have 2%, even if 2% of them are fluently inadequate, when the denominator is millions, that's still tens of thousands of problematic translations. And our system analysis showed that this is an issue that affects all the models considered, but they happen more for the in-neural models, especially when translating out of domain, translating text that is very different than the text that the models were trained on, and especially for lower resource languages where the translation quality is poor. So that's definitely something that we need to pay more attention to, we need to detect better, and then of course we need to figure out how to address the underlying issue, how to improve our models so they don't make these kinds of errors. So that's one way in which we can make neural models more responsive to user needs. I want to very quickly tell you a little bit about another project that takes this question in a different direction. We've been asking recently how we can build systems that are more, that adapt the output more to the audience of translation. So one way we can do that is make machine translation systems sensitive to formality. Maybe I want to have a system that for the same French input translated differently depending on whether I'm in a formal setting or an informal setting. Or maybe I want to translate differently depending if I'm translating for a fluent English speaker or a second language learner that might just want to have the core meaning across, doesn't care about all the details, might want to have simpler words and a simpler sentence structure. So we came up with a method for doing this kind of translation, where we treat the task of converting complex language to simpler language, or converting formal language to informal language as translation. And we are able to train in a supervised manner a model that learns to do this transfer at the same time as it does translation. And so it makes the model a bit sensitive. It makes it possible to control the style of the output as part of the translation process. So these are promising case studies, but again, there's a lot more we can do. We are not able to control the nature of the style transfer operations very well. And our approach has a lot of requirements in terms of the data to be able to work. In particular, we need to have examples of formal and informal language paired together for supervised training, same thing for complexity. And it would be a lot easier if you could do this in an unsupervised manner. So that's something we're looking at currently. All right, so to wrap up, I started by explaining how deep learning model, deep neural networks provide a powerful framework to model translation. And they power all the translation systems that are deployed today. I talked about different learning paradigms, supervised training, unsupervised training, and explain how the middle ground, semi-supervised training, is key to train high-performing models in realistic scenarios today. And finally, I talked about two studies where we try to make these neural models more responsive to user needs by detecting problematic errors, like the fluently inadequate outputs that I talked about, and also by trying to broaden the task that the models are asked to perform and asking them to be more flexible to adapt to different audiences. So this concludes my talk, and I'm happy to take questions.
Brilliant. Thank you so much, Maureen. We've had a couple of different questions come in on the Q&A. So if you don't mind, I'm going to ask you one that addresses the question of sort of formal versus informal language that you just wrapped up with, which is, again, super interesting. So the question is how does unsupervised learning deal with new language styles amongst young people, for example? So do you use this same technique to translate between formal and informal to address sort of older versus younger styles of language? Is that a possibility?
Yeah, so that's a great question. So language changes constantly, right? And so that's a big problem for our models that are just trained on whatever data we have. And when new words or new ways of using existing words come up, if they're not represented in our training data, we just don't know how to handle them. So to deal with that, there's sort of two approaches. One is to constantly kind of refresh the data and try to incorporate more newer data as much as possible. And so we can do that both in the supervised setting, which requires examples of translations, or in the unsupervised setting, where if I just have, I don't know, if I collect data on Twitter, maybe targeting younger population, I can throw that into my model, maybe using back translation as some kind of semi-supervised learning technique, and that's going to help me do a better job. So in the style adaptation I talked at the end, we haven't looked at specifically at this scenario. Most of the way in which we adapt system right now is kind of, we don't explicitly characterize, is this, language of younger people in this particular demographic group. We just collect data and let the data drive the kind of language we're producing. So for instance, if I say formal and informal, that's kind of defined by the data I use to define formal and informal. So my particular data set came from Yahoo Answer forums for the informal language, and then we had a formal version of that. But that's not all of informal language. So that's kind of a key issue right now, which is that whatever we use is kind of implicitly defined by the data. Whatever dimensions of language varieties we want to work with are just implicitly defined by the data we're working with. And trying to generalize to, all the population and all possible language styles is tricky. Because whatever style is dominant in the data will dominate what our models produce.
Great, that makes sense. And there's a question that then addresses almost exactly what you said about building more data, getting more data to help you to answer some of these questions, whether formal, informal, younger, older, et cetera. And that's is that given the significant training data sets required for building either supervised, unsupervised, or semi-supervised models, is there always a risk of the content that's being translated being compromised through the process of gathering data? And the related question is, well, it seems like maybe you would end up having to store quite a lot of that data in order to be able to improve these translation systems over time. So as a user, should we expect that when we use a translation system like this, that the queries that we've made are automatically going to be stored in order to improve this over time, or to help a researcher such as yourself to improve your systems before they're widely deployed?
Right, so there's sort of two, like there's a data, so there's kind of the training data, right, the existing translation data, that typically what is used in systems today is a lot of data that's online and that people scrape, to power the systems. There's the issue, different issues arise when you want to translate more proprietary data. When you don't want that data to be shared. There are ways of adapting the models just to that data and also leveraging the existing public data. But then there's also the question of adaptation. I think what you were raising at the end, for me as a researcher, it's very useful to have a record of the translations that were produced before, the queries, and there are systems like, for instance, Google Translate sometimes gives you the option of correcting the output, right? If you can read the input, you can rate the translation or sometimes correct it, and that's a very useful signal to improve models in the future. But that's not always something that you want to share or you want stored or you want to have control as a user in how this is used. So there's a little bit of a tension between, on the researcher side, we'd like to have as much data as possible, as much of it public, and we'd like to have, ratings and corrections. We want to get as much information as we can to build better models, but at the same time, that there's a question of how to do that, how to build better models using that information, but what to do when this information cannot be shared. There are other issues that arise in terms of models, which is that there's a kind of a feedback circle that comes in when there are websites that are built using machine translation, for instance. And then when we go and crawl data, we might add that to our training data. And so we create a feedback loop where our system is trained on machine translated data. And so that can be an issue. And there's work on trying to detect when this happens, when the translation are noisy or incorrect, try to filter them out. But when we're working at scale, when we're trying to crawl the whole web to find examples of translation, there's always going to be noise that comes in.
That issue of sort of machines translating machine translated language is definitely one of those interesting things. I think there's a very fascinating piece that we saw came out from MBER recently about the increasing use of machine translation for corporate reports and how that may cause sort of an iterative loop. We have a couple more questions in here. So obviously you are really firing up the audience, which is great. All right. So one of the questions that came in would be, you mentioned something about this machine translation not being a solved problem, right? How do we know when this is solved? What's the apex level of accuracy and translational fluency that you're aiming for? Certainly we can strive for 100%, but we're probably going to run into Zeno's paradox somewhere along the line. Where should we go and where should we aspire to for this?
Yeah, that's a great question. So there's been a lot of controversy in the field, among researchers behind. There's this push for achieving human level translation quality, but it's not clear what that means. Different humans are going to translate differently, and so it's not clear whether trying to mimic humans is really the most useful thing to do. From my perspective, I think I want the technology to be useful. And so it can be useful even if it makes error. And I think it's always going to make errors. Even the best translation systems that can sometimes produce or often produce translations that are indistinguishable from human translations make errors, make the kind of fluently inadequate outputs that I was talking about. So I think to me, the question is, how can we make machine translation useful? And there are ways in which it's already useful today. Many professional translators use machine translation as part of that process. So in different ways, depending on the genre, maybe if you're translating poetry or a novel, machine translation is not going to be very useful. But maybe for translating very controlled language or technical documents, machine translation is useful. I think machine translation is also part of the workflow, for instance, in the EU translation process. So it can help make humans more productive, translate faster. There are issues in how to do that properly, but that's definitely one path. I think translation is also useful when it helps people access information that they would not have access to otherwise. But then, how to deal with the errors it makes in these scenarios is an open question. So I think to me, there's no, I guess I'm not too, my goal in research is not to replace humans, but to figure out how we can make it useful. And I think there are many ways we can make machine translation useful, even if we don't reach human level translation accuracy.
Great. So I'm going to take one more question out of this, and it's going to address something that you just sort of hinted at, and that is sort of dealing with the context of the European Union, right, and machine translation and how that might help. So obviously, we've got a lot of our viewers who are going to be worried about what's going on within the EU's guidance on use of AI, et cetera. So what should we know, or should researchers be concerned about changes in terms of EU GDPR type of regulations for the flow of data for training systems such as yours? Do you have any concerns about that? Do you see that that's going to be something that helps and or hinders your research?
So I think it's a challenge, and so I personally, in the research community as a whole, in machine translation, we haven't really thought about it seriously. We just gather as much data as we can and just train on it. But it's very hard to figure out how to implement, for instance, removing data, tracking which data is used, and how it impacts a system. When you have, 10 million training examples, if there's data that needs to be removed, It's not clear to what degree it influences the systems. Retraining a system from scratch is also quite expensive. So there are lots of issues there. But I'm, I have to admit that these are not issues that we've thought about seriously as a research community. So I think that's an open question.
All right, well, thank you so much. That was absolutely fascinating. I know I learned, obviously many of our viewers have learned here based upon the questions. Let me thank you very much again and shift over to Rob, who will tell us about the next steps at our masterclass.
Thank you very much, Sarah. What we'll do is we have a short bio break. We can stretch our legs and we will reconvene at 5 minutes past the hour, where we will start the fascinating presentation by Dr. Prem Natarajan. So back in 5 minutes. We're back. There we go. Next, we will have the pleasure to say hello to Dr. Prem Natarajan, the VP of Alexa AI NU. He's the Vice President in Alexa and leads a multidisciplinary science, engineering, and product organization, which improves customer experience worldwide through advances in dialogue modeling, natural language understanding, entity linking and resolution, and related machine learning technologies. With that, I'm going to give the floor to Dr. Natarajan. And let me see whether I can also give you the controls of my screen, and otherwise I'll ask you kindly to guide me to the next slides.
Thanks, Rob. Good afternoon to everyone. Can you hear me clearly, Rob?
Yes, I can hear you loud and clear.
Great. Okay. So, so today I thought I'd set the context first with at least how I, in any testimony of history, is always a little personal. So this is sort of my sort of take on what was salient and what were the important historical developments over the last especially over the last 4 or 5 decades, but putting it in the overall context of evolution of AI. And then what I consider to be the transformational advance, and I don't think I'm alone, in that AI really started showing its potential when we were able to combine machine learning with what we tend to call AI, even though the two terms are used interchangeably oftentimes. And then I thought we'd take a quick look at Alexa, sort of how Alexa embodies machine learning powered AI. And then something looking forward that we're all excited about, which is learning with less labeled data. We haven't quite figured out how to learn with less data, but we're starting to figure out how to learn with less labeled, manually annotated data. And then last, I always like to end with something that inspires me, which is sort of the societal impact that AI can have. And in this context, a couple of examples of how Alexa has made a difference to individuals. Next. Actually, I'm going to try. So this is sort of, as I said, a very brief look. I have a longer version, but for this session, there's a more compact version that I'm presenting. Next. Yeah. So, interestingly, and I'm based in LA now. I've been here for sort of the last 7 or 8 years. And it's always interesting to me that the place of Hollywood is where also some of the earliest work in AI happened, largely because of the nexus between Caltech, Stanford, and the other universities in the Southern California region. And Willis Ware, who was the chair of this very first session on learning machines. And back then, the AI field was really sort of people researching the neural structure of the brain, what they could at the time with available techniques, and then how to create machine implementations of what they understood. And this sentence, which I often put in front of audience's interest. I find it interesting because he said that there is considerable promise that systems can be built in the relatively near future, which will imitate considerable portions of the activity of the brain. And this was in 1955. And in some sense, that statement remains as true now as it was in 1955, which is about 65 years ago. Next. So this slide is not meant to sort of be literally read, but the point I wanted to convey with the 2 points I wanted to convey with this slide. This is a timeline, as most of you can see. The top half above the center line is sort of what I consider general AI milestones. And the bottom half shows sort of the natural language processing, including speech, as sort of contributions to that timeline. As I think what's interesting is right from the start, from when AI became sort of being envisioned as an area of research, natural language has been right from that time sort of a salient application area for research, and it has continued all along. And some of the most sort of practically impactful advances have come from AI applied to natural language processing. Second thing is, AI has gone through, just like markets, through these cycles of intense optimism, and then some amount of pessimism, and then optimism again. And so we're now, in my mind, in the third sort of period of optimism. But from like about 1950 to mid 1970s was the first major era of optimism, followed by what now looks like a brief winter. And then the second AI winter was similarly 87 to 93. And then from 93 onwards, it's sort of not been that extreme. It's always been a little bit hot, a little bit cold. But the last 10 years, without question, I consider the AI spring. So let's go on to that section. Next slide. So this slide shows you the last essentially 30 years. So if you look at these AI milestones, again, on the top, you see sort of what I consider general AI milestones, not specific to natural language processing. And then the bottom half shows you the natural language processing aspect of it. I still distinctly remember trying Dragon Naturally Speaking when it came out and being impressed that you could actually move forward and backward between command mode and just editing. So you could just dictate a letter to it. And then if you wanted to delete the last 3 words or correct the last 3 words, you could just say, delete last 3 words. And it was able to do that. And back in 97, to me, that was just a stunning advance in sort of the practical usability of speech recognition. First time I at least became deep down convinced that speech is maybe ready for prime time. Then 97 was also this major thing. Today we think about AlphaGo, but in 97 it was IBM's Deep Blue beating Garry Kasparov in chess. It turns out chess is somewhat easy, as it turns out, relatively speaking, in terms of machine learning. And that's a retrospective perspective, of course. Forwarding over to this decade, I think sort of 2012 was the major milestone when deep learning was demonstrated by Hinton and his team, beating the state of the art for object recognition quite conclusively. And then, of course, there was a gold rush to see what else can it be used for, and that gold rush hasn't quite ended yet. We continue to be surprised. We continue to learn from the operations of these systems. A few years ago, generative adversarial networks came in that said, maybe we can actually use these networks to sort of teach themselves too, and sort of regulate themselves. Then forwarding over to 2020, I'd say a couple of excitements from a personal perspective. One is the launch of Teachable AI, which is the first time that there is a broadly launched capability that allows users or users of the AI system, in this case Alexa, to directly interact with the system and to teach Alexa new concepts. And also natural turn taking, which blends multimodal signals, visual, text, speech signals, to allow people to have a multi-party conversation with conversational AI. Both of these we did public demonstrations of at the December Devices launch event in Seattle. The other thing to take away from the slide, those three curves that you see, the blue one shows you the increase in algorithmic complexity. The sort of orange one, if you will, shows the increase in sort of the data. This is largely because so much is instrumented today. And then the yellow one is the increase in processing power. It's actually the fact that all of these curves have a monotonic and sort of near superlinear growth that has in part enabled us to come to this golden age of AI. Next slide. Where, essentially we're now able to apply all of these advances to nearly every area of human endeavor in today's world, whether it's precision medicine. My friend Greg Versteeg at USC applied information theoretic approaches to deep learning to actually customize cancer treatments for individuals. And one of the first patients who benefited from that went on to start her own consultancy where she helps other patients similarly discover treatments customized to themselves, all the way to the other end of the spectrum, which is dating apps, finding your life partner, hopefully, and then all the other applications that you see here. Next. So as I mentioned in the introduction slide, I think a lot, AI and machine learning, we often use them interchangeably, but I sort of make a small distinction into machine learning as a methodology and AI as sort of the capability that we're delivering that performs certain tasks. And AI in general could perform those tasks with or without machine learning, but it's the advent of machine learning that has really powered all of these transformations in AI capabilities. Next. So to take a look at this, actually, let's go to the next slide first and then come back to this one, Rob. Okay. So this, I think across all the different AI applications, I think one of the common themes is data-driven machine learning. What I mean by that is that this methodology is replicable to many, many tasks. You just heard Professor Marine Kapua talk about machine translation. And that could be one of the tasks which, I'm not listed it here, but at its core, the methodology is relatively straightforward, which is you have a task, let's say it's speech recognition, your input is a speech signal, and the desired output is a sequence of words. So we call those the answers. We can call the input the questions if you like. But our goal is, in comes the speech signal, and I'd like to produce this answers. And the methodology is, let's get a few folks who are just practitioners of the language. They don't have to be linguists. They don't have to be experts in any aspect of language processing, but they just take the speech and they write out the sequence of words, the speeches. From that, the trainer, which is at the bottom of this picture, right, learns what it calls a model. Sometimes in colloquial things, people like to call it the brain, etc. But it's so much more limited than a brain. So from that, the inputs and the answers, the trainer learns the models. Those models are then used by the runtime inference engine, or what is called decoder in some technical literature, where the input comes in and the models are used by the decoder to generate the answers. This basic methodology has been repeated to numerous applications. Sometimes it's sequences of words, sometimes it's putting labels on specific portions of the sequence, as in natural language understanding, outputting intents and slots. Other times it's object recognition. Let's go back to the previous slide. So the technological evolution that has happened in machine learning over time is that, all the way to the left of the slide, you see these rule-based systems. Okay, so these rule-based systems were just sort of handcrafted, extremely handcrafted, both the features and the way in which inference was done. as you progress on the slide from left to right, all of those are different forms of machine learning, just with different capacities to learn. And if you notice, neural networks actually came about for the first time seriously in the 1980s. And in fact, Jan LeCun had a couple of papers back in the 1980s presenting convolutional neural networks, which are, I think, required reading for any student in this field because of I'm always impressed with how much of the future of the capabilities of these techniques he anticipated in a couple of those papers back then. The problem that they had back then in making these things really work well was lack of compute power and lack of adequate data to train these models. So then the statistical models, and especially hidden Markov models, took over. Then you got all these kernel techniques with SVMs and random forests, etc., until about 2012, when deep learning came in. The other interesting thing to look at is all the way up to, I'd say, SVMs, we were very reliant on handcrafted features. So people who had a really good understanding of the domain would would have tremendous sort of capacity to handcraft these features that would increase the discriminative powers of these models. And so a lot of it was not just pure science. Some of it was art in how people handcrafted those features, and the rest of it was science. But you also had good interpretability. But back then we used to complain about the interpretability of hidden Markov models, but now we don't. But with deep learning, everything became automatic. You know, the expertise required to handcraft features, along with the fragilities that implied, sort of went away. The computational power increased, as you can see in that graph. Recognition errors really reduced dramatically, which is what made us very optimistic about being able to deliver real-world applications. Next, then you can skip this one. Yeah. So of course, I'm sure this audience knows that supervised machine learning, which continues to remain the state of the art in terms of the performance that you can deliver given adequate training data, is also the most commonly used version of machine learning. So you start with unlabeled data samples. Annotators will go and put in labels on the samples, which gives you labeled data samples. You train your models, and then the runtime system consumes those models to automatically produce labels on new test data. Next, just click once. So you have, this is just a simple example as to how low intensity the labels can be. So you have all these various pictures of cats and dogs, and you label them with just the name cat and dog. Now, interesting thing is each of these images actually contains more than just the object of interest, but you don't have to go and actually draw boundaries around the objects of interest. One of the major advantages of modern machine learning is we can learn the segmentation along with sort of the specifics of the object, along with the background, without requiring anybody to segment, to provide the segmentation information, right? And then in comes your new test data on the right. The model uses, the runtime inference engine uses the ML model and produces the prediction dog. This is sort of classic supervised machine learning. Next. So we just sort of, as I mentioned, a brief look. So we looked at what I consider, and I think a lot of other people do, transformation in AI, which was sort of the advent of machine learning, starting circa, let's say, early 1990s. And then, but the distinction, but there's no question that everybody believes that the current profusion of applications is driven by advances in deep learning. And so what's different about deep learning? As I mentioned, it's really in the fact that the feature design and the model training are done jointly, right? That nobody needs to go in and handcraft features. That was a major bottleneck. It's now easily forgotten. We now have like almost a generation of scientists that we've produced, because a standard PhD takes 6 years, and all of this happened 8 to 9 years ago, who have forgotten how much time and how much effort feature crafting took, and how much research effort was focused on that. So now all of the research effort has moved into sort of the architectures of these networks, the different kinds of error functions that you can use and how they modify the behavior of these models, and then what we call hyperparameter optimization, how the top level meta parameters of these models, the configuration, et cetera, influences the behaviors of this model. So the research has sort of been abstracted out to the next level up. Next. So in my mind, it's really, all of these applications were envisioned even in the mid to late 2000s. What has really made it possible for all of these areas to get benefits from machine learning is this advance of machine learning powered AI, and specifically deep learning powered AI. This is just a set of areas where I think it's particularly noticeable, but everybody has personal stories about where the impact has been. Next. So this is just the next few slides I'll breeze through. It's just to show how some of these techniques powered Alexa. Next. So looking at human computer interfaces, I often feel like looking at the evolution of things always gives us good context. So, human computer interfaces have advanced in roughly decadal leaps. Like every decade, there's been some kind of major advance, which means I think we're on the threshold of the next one sometime in the next few years, perhaps. It started off with character mode interfaces in the 70s, graphical user interfaces in the 80s, web, mobile. Now, the thing with all of these was, with the web, you could sit at your home and you had a window into the world. With the mobile, sort of the window went with you, traveled with you, and you could have sort of your window wherever you were located at the time. With voice, the major transformation is you don't have to touch, you don't have to interface, you just talk to your environment and your environment talks back to you. And that was sort of the magical advance that Alexa delivered in 2014. Click once. And this is sort of what we call today conversational AI. Next. Again, within that overall historical context, here's the conversational AI timeline. All of these things, when we're at sort of at the edge of this innovation, everything feels accelerated, but all of this has taken multi-sector participation over many decades, starting with investments by NSF and DARPA in the US and similar agencies in the rest of the world. In Japan, the government made massive investments in the 5th generation computer systems, starting in the 80s. Europe has funded huge amounts of research in this area for the last several decades. All of these are essentially the platforms upon which all these advances stand, in a sense, right? Creates talent, creates advances, creates new insights, and from that we learn and do make new advances. But the interesting thing with speech is people have always wanted to use it for something practical, whether or not the technology was. So there's always been this sort of product mindset or trying to make it useful for humans. So back in the 70s, right when it was very low vocabulary speech recognition, 200 words, 300 words was sort of capacity. People were already imagining the voice typewriter and starting to try to build it. Then you come into the 90s where we said, okay, now we can actually get a few thousand words reliably recognized correctly. Name dialers came into existence. And I remember back when I was at BBN Technologies, for many years, we had a corporate name dialer that was built using our own speech recognition, where you could just pick up the phone and speak somebody's name and it would connect it to you. And that was a major friction reducer. Then in late 90s, early 2000s, there was all this automation and directory assistance call routing. And then, in fact, the Jaguar S-Type 2000 had the first in-car speech recognition with the technology that my team had created back then. Then, of course, we've talked enough about the modern deep learning thing, but now you can see sort of the transformation from very simple, very narrow applications to much more broad-based interactions, much more capable systems that are able to answer questions, provide information, take actions on your behalf, etc. Next. Our mission, my organization's mission, Alexa's mission, is to build AI technologies that make Alexa the most natural, competent, and trusted personal assistant, advisor, and companion for all customers. And we want to do this by advancing the state of the art in general intelligence in a way that allows us to deliver the best customer experience that we can. Next. These are just, this is just a component view wake word, automatic speech. The point behind this is all of these are built with the same methodology that I described some slides ago. Next. This is what happens when you say something to Alexa. You say, play Message in a Bottle by Sting. The utterance comes in, goes through the ASR, recognition result comes out, and the natural language understanding system takes over and converts that recognition result into intents and sort of the arguments of that intent, which is what might be the song name, et cetera, sends it back. And then the system both takes the action, which is to play the song, and then also produces a spoken response that tells you what it's going to do for you. Next. In terms of the advances that have happened in the 6 years since it's been launched, starting off with a dozen skills or something over the last 6 years, we have increased the number of skills which are really developed by developers all over the world, not Amazon developers. Number of skills has just exploded. There's 100,000 plus skills growing every day, hundreds of thousands of developers. And so one of the things we feel proud about is about democratizing AI. None of these skills developers could actually develop conversational AI-based applications if they had to develop the whole stack from scratch. But through the skill developer interfaces and toolkits, we can actually allow them, enable them to develop hundreds of thousands of skills. Second thing that we're particularly proud about is while the number of skills has gone up, the error rate has come down. Otherwise, this would be bad. Like you can do many more things and they're all much worse. But right now we do more things every year and we do each of those things better every year. And all of this takes a fair amount of research in AI, in machine learning, and also in sort of the tooling and engineering to deliver those development capabilities to our developers. Next. So now, the topic that I really wanted to share some thoughts about, which is learning with less labeled data, where we're going beyond supervision, right? Supervision remains state of the art. If you're given adequate training data, it's very hard to beat supervised machine learning. That's going to probably be the case for a while. Next. But the promise of less labeled data, especially deep learning, is what has allowed us to really accelerate research into the use of less labeled data, as I'll tell you in the next few slides. The promise of using less labeled data with deep learning is that we can come close to the performance of supervised machine learning with much less annotated data. We still need lots of unlabeled data, but we haven't figured out how to not do it with data, but we can do it with much less annotated data. And on the right here, what I'm showing is some of the major areas of research today in terms of reducing the amount of annotated data required. Active learning techniques, then this whole area of transfer learning, cross-lingual projections, etc. Semi-supervised learning, particularly useful for things like speech recognition and computer vision. Self-learning, and then teachable AI, both of which are particularly useful for deployed applications where customers are interacting with these capabilities. Next. So first with active learning, the idea here is very simple. If there are, you see red and blue, first focus on the red and blue in this diagram, in this graph. It's very easy. You can very quickly learn with just a few samples how to process with near 100% accuracy samples that fall where the yellow and blue ranges are, because there are so many lines you can draw that separate them out. But there's always the hard machine learning task is these things in gray, these crosses that you see in gray, which represent samples that are at the margins and ambiguous. And which means that's where most of the new information is for a classifier or a predictor to learn. And so we have invested a fair amount of research effort into figuring out active learning techniques that work particularly well for speech recognition, natural language processing, etc. And in some cases, we've actually achieved a 40x reduction in the amount of training, in the amount of annotated data that we require to achieve the same level of performance. Put differently, that basically means what used to require 1,000 labeled samples can now be done with 25 labeled samples. That's not for everything, but there are certain tasks for which we've been able to do that, and that's a huge win. And in here in the slide is one of our papers by our scientists, and you can go take a look at it on it's also available on archive. Next. The next one is transfer learning, and I'm going to have a couple of slides on transfer learning. One is this, where the whole notion of transfer learning is you have domains in which you've invested in collecting label data, you've trained those networks, and then you want to sort of take the results of the training over to new domains or to new languages where you don't have quite as much data. So there's a whole bunch of techniques that we call transfer learning, where you can start with the starting point of the training for the new domains can be these trained networks. There is, of course, a fair amount of technical detail to how it's done. But the interesting thing is we're also able to do it across languages, not just across different applications in the same language. And across languages, there's a few different ways to do it. One is to actually force the network itself to abstract away some aspects of language and to learn language agnosticity into some of its internals. The other is to use techniques like machine translation to actually project training data from one language to the other, and then use those projected training samples to improve performance. Next. This is sort of now, a lot of people working in machine learning know about this. In the last couple of years, there's a lot of excitement around what we call pre-training, which is you can use large amounts of data from any domain to do what we call, to train what we call a pre-trained network that is not particularly great at any specific task, but it's great at representing the information in language. Then you take a small amount of task-specific data and you fine-tune that model. And in this particular case, you can go, this is not our work. The example that I've chosen is from the Insight data science blog online. And in this particular case, the author actually presents the details of what he's done. You can actually get, just with 500 samples, what took thousands upon thousands of samples before. And here he's talking about how he was able to get to 83.3% performance with just 500 samples. Next. A related technique is semi-supervised speech recognition training. The core idea here is you train a large model, and then you use that large model to train a smaller model that mimics the performance of this large model. And therefore, we call the large model the teacher model and the smaller model the student model. If you click one more time, a first of a kind experiment that we did, and we reported it at a scientific conference in 2019 at Interspeech. Nico Strom, one of our distinguished scientists, was sort of the primary driver behind this work. We took 1 million hours of unlabeled speech data, the first time any training has been done with that size of data, and coupled it with a small amount of labeled data, and showed that we could get improvement over a model trained with much larger amounts of labeled data. And so this is now something that we use in many, for many of our speech recognition capabilities that we provide to customers, because we are able to use unlabeled data, which is very efficient for everyone. There's computational costs, but there are other benefits to not having to require labeling. Next. Learning to paraphrase, I'll just let you take a quick look at this. It's basically, can I learn to restate, if I can't understand a question as it's stated, can I learn to find an equivalent statement that I know how to answer? And that's the fundamental idea behind paraphrase. Click once. The first pass, is Bosnia still a country now? Maybe worded in a complex way, and it's not able to get the answer, and it says, I didn't understand. Click again. But the next time you do it, it understands it, because it was able to get a paraphrase which says, is Bosnia a country, comes back, and then it can provide you the answer that yes, Bosnia is a UN recognized, and Herzegovina a UN recognized country. Yeah. Okay, next. Next is self-learning in the field. You might say something like play the ABC song. Maybe Alexa has never heard the ABC song, so it doesn't understand. But maybe you follow up with a question that says play the alphabet song, and maybe a few other customers do it. Using signals like these, we can automatically learn that play ABC song is the same as play the alphabet song, and that ABC song is equivalent to alphabet song, which can be used in other contexts. In this thing, the thing I love about this is this works in the field automatically with no human intervention. And within like about 14 months of its deployment, it's correcting millions upon millions of defects every day, every month in the field out there for customers, with no human intervention at all. In fact, none of us exactly know all the different corrections that it has learned because of the speed with which it can learn just on its own. Next. This is just a slightly more detailed technical view of it, which is when you're doing this stuff, you first have to detect that there has been an error. Then you have to figure out how to automatically reformulate the query. And this is where we use the signals directly from the customer. There's no human intervention. And the feedback can be implicit, or we can ask the customer, is this what you meant, to get confirmation? And then we learn that in this case, SiriusXM chill is the same as SiriusXM channel 53. And going forward, you can always answer that question for any customer. Next. Teachable AI, something that's near and dear to my heart, something that we launched just a month ago for audiences in the US. This one learns new concepts and preferences directly through interactive teaching by customers. So imagine you say, Alexa, play this song at full blast. Alexa doesn't know what full blast is. Instead of saying, I don't know how to process that request, she comes back and says, I don't know what full blast means. Can you please teach me? And then we say full blast means maximum volume. And then Alexa says, thank you, playing song at maximum volume. And the next time it learns that full blast is equivalent to maximum and can apply it in different contexts. Also, we have deployed some, and you can, folks in the US can try this. Alexa, it's cold in here. If you've linked your thermostat to Alexa and you just say, Alexa, it's cold in here, Alexa will come back and ask if you should increase it. This is sort of our fledgling steps into common sense reasoning, where when somebody says it's cold in here, we know they're not just complaining, but they're saying, can somebody fix it? And then we sort of figure out what is the right fix in this case. Anyway, next slide. Okay. All of these things together, this is just my wrap-up slide for saying how things are going. I view the progression over the last few decades as moving up at the AI stack. At the bottom of the AI stack is sensory data and directly relating sensory data to actions you want to take. The next step up is phenomena modeling. This is where there's a speech signal and we want to say what is the speech recognition output. And this enables a simple set of applications like transcription applications, etc. The next step up is contextual decisions. Hey, somebody's asking me something and I want to take an action based on that. How do I make that decision? What is the best action that I can recommend to this person? And that requires the use of context. And so it's a contextual decision-making capability that builds on top of phenomena modeling and other AI capabilities. Then, of course, the next step up is reasoning. And I think we have a long way to go before we bring reasoning more fully into all of these AI systems. But that's where a lot of the exciting research is. And ultimately, of course, there's autonomy, where you have AI agents, learning on their own, learning to even do new things on their own, etc. This is still in my mind. I'd be delighted if I saw some really strong examples of autonomy before my time on this earth is over. So I still think autonomy is, except in very specific and narrow instances, very hard to achieve right now. Next. So last two slides on societal impact. This always inspires me. Next. One is this child, seriously challenged young individual who there's a Dynavox device that is how he's able to generate speech. And all he can use is that one finger on his left hand. And he had never been able to independently communicate or ask for anything. But one evening, his parents were out at a movie. And Jaden somehow managed to use the Dynavox device to generate a call to his grandfather to ask him to come and give him a car ride, which turns out to be his favorite hobby, to go on car rides. And so his grandfather came over, of course, was very surprised and took him out. And it was a major emotional moment for the family. It's just one individual. And there are many other stories like this that come about, but this one has particularly struck with me because it to me is sort of the North Star for AI. How can we help elevate the human condition through our work? Next. A different example, which is more at scale from India, is the student Amol, is this teacher Amol on the left there, and his co-teacher. But Amol had this idea of using Alexa to teach English to his class, basically incentivizing them. And he did his own interesting thing by creating this avatar for Alexa that's just his own creation. Students in his class are rewarded by being able to talk with Alexa for a longer period of time if they do well. This has actually inspired us to create new capabilities for teaching in India, things like how to spell certain things and how to adapt to the local accents, etc. So sometimes all of the societal impact that people imagine, which we don't imagine, but users imagine and apply to, comes back to us in the form of research challenges that we can work on. And that is also inspiring for us, and especially for our team in India. With that, I thank you all for your attention and happy to answer any questions that Rob might have or others might have.
Thank you very much, Prem. A fascinating presentation there. I have a fire starter question, and I also have my colleagues Brenda and Sarah that may jump in after that as well. Could you tell us more about semi-supervised learning? How much do you think it will change the way data are humanly reviewed by AM/ML purposes?
I think I see semi-supervised learning as sort of on the beginning of this curve of moving away from supervision or greatly reducing reliance on annotated data. Semi-supervised learning is already in production, so it's already hugely reduced the amount of data that we require for speech recognition training. Now, I want to be careful. It doesn't require the amount of data you need. It reduces the amount of labeled data you need. In fact, in other words, you might be able to do with X hours of labeled data, some level of performance, and now you can do it with maybe, I don't know, 0.1x of that data. But in return, then you need 5x times the unlabeled data, right? The advantage here being it's only the machines that process that data, and it's never needs to be looked at. Same with active learning. Active learning is also in production for different kinds of learning techniques, and that also, again, helps us minimize review. The next step up, of course, were all the other things I was talking about, this transfer learning, and then the unsupervised learning, and then the self-learning. So all of these, in my mind, are a spectrum, Rob, where we're starting with semi-supervised learning and active learning. We're then augmenting that with transfer learning to say, if I've already labeled data once, how do I maximize the benefit of that labeled data for many, many, many other cases, right? So one is reducing the amount of labeled data. The second is maximizing the impact of any data that you label. And then finally, actually just learning directly through interactions. And this also allows you to, in the end, become sort of a personal assistant, because each person may teach things differently and how they want stuff done. And so that's how I see this progression. We're on the start of this major revolution, and the next few years we will see this accelerate.
Sarah.
Good. Thanks so much, Prem. I really appreciate that. I wanted to actually shift and ask Maureen, as somebody who's within this field, right, if you had any questions that you'd like to ask of Prem, recognizing the need to, value our experts here first.
Thanks. So thanks for a great talk, Prem. I guess as someone who looks at translation and multilinguality, I'm always curious about porting technologies to all of the world's languages. And so I'm curious, what are your thoughts and where Alexa is at this point in terms of working not only in English, but also in other languages?
Yeah, we now support more than a dozen languages, right? It's been an interesting progress for us from, when I joined a few years ago, we had 2 languages. We're now at more than a dozen. There are a couple of things that come in. One is, simply proving or demonstrating that certain capability can be ported to a new language. And that's relatively, I think, straightforward to do for some cases. Not so straightforward for some other cases, like where you need parallel corpora like machine translation. Now you're not asking for just label data in one language. It actually requires bilingual speakers who can annotate data, etc. And so it's a little bit of a bigger reach in some of those instances. But for us, what we really want is not just the ability to do NLU or ASR in a new language, but the ability to do it well and well enough that customers are satisfied with it and that they find value in it. And so going from that point of saying this language can be supported to saying where this language can be made useful, that support in this language can be made useful to the customer, is where most of our work is focused. And that's sort of the thrust of all this research in transfer learning, semi-supervised learning, et cetera. Now, one both challenge and advantage we have is that we need to make it useful, but on the other hand, we also have like a pretty good sense of what that usefulness means. So we have good ways, good like concrete optimization targets, right? Whereas if you're working, like for example, imagine somebody is developing machine translation and their application is just news, right? They in principle have a simpler task than you might have where you're trying to do general purpose machine translation. So I think it's both a challenge in that the performance has to be really, really good for customers to benefit from it. On the other hand, the fact that you have certain capabilities in mind gives you very concrete optimization targets that allow you to design techniques that work for those specific learning tasks.
So I have a question to come to both of our speakers. So one of the issues that seems to arise in the context of machine translation is that sometimes the machines teach themselves an intermediate language in order to be able to facilitate translation, say, between English to French, English to Russian, Russian to French, et cetera, et cetera. Is that something that is of concern? Is that something that challenges some of the performance dynamics, whether or not of an Alexa system or of a research system? And well, we often read about those in news reports. How real is that phenomenon of the machine intermediate language? Happy to have an answer from either of you on that, or both.
I'm happy to take a shot, but I was wondering if so I think there's something technical about language. I just want to sort of first sort of characterize the question a bit. Machines, I would say, learn intermediate representations, right? I'm not sure that I would characterize that as a language. In the sense, I don't think those intermediate representations necessarily form a complete sort of language of their own. Like if we sort of try to learn it, that we could make sense of it. Forget that it's all numerical, etc. I'm not even getting into that. Just that the structure and the shape of those representations may not be a language, right? In other words, they provide some anchor points, but you actually need languages at the two ends to actually constrain the potential set of interpretations that could come out of those representations so that they can be language. So in some sense, I don't think these interpretations exist on their own, except in some very specific instances. So if you take like object recognition, right? You could, in principle, learn a somewhat language agnostic label for cat, that then you separately learn what cat is in a new language, and then it can still label that image as cat in a different language. But you still need that language target in the end to sort of contextualize that representation that it's learning. Marine, you were nodding. I thought you wanted.
Yeah, I agree with that characterization. I think it's important to draw that distinction between like internal representations and language. I think another thing that arises is a little bit different with these types of models, and the language that produce kind of normalizes in a way, what is seen in the data. So that's not exactly the question that Sarah was asking, but in the output of the systems, they produce a form of language that is, it might be well-formed, might be great English, but that is a little bit more narrow, perhaps, than the English as a whole. That might just represent the dominant forms of English in the training data, right? So that might be along demographic lines. Maybe there's more language written or spoken by male adults And so that's going to be the dominant form of language that's producing the output. But it might also be in terms of domains. Maybe we have more data that is news in our training data. And so we're really good at producing news-like language, but there are many other forms of languages. So that's not the question Sarah's asking, but I think there's also another way in which systems kind of manipulate the language that they might produce a little bit.
Yeah, if I can just add, I think you're right. On the generation side, I think different issues come up from the understanding side. I mean, with understanding, you're trying to interpret the many ways in which humans are generating, but in the end, humans are generating it. So in some sense, it's grounded in a physical world we live in. And so that grounding is important. But going back, Sarah, I just wanted to, as I was listening to Maria, I was thinking back to, maybe 30 years ago when there was all this work in something called interlingua, where, and I think maybe that's what you were channeling. And so, at one point I remember where there was a proposal saying, how about English as the interlingua? So we learn to translate from all languages to English, and then English is our language representation. And then we learn to go from English to every other language. Well, there are obvious issues with it. Not all languages have tense. Not all languages have the kinds of inflections that you do. So it turns out there is no existing language that is really a complete basis for any other language. So I think it's hard to come up with an interlingua in that sense, which is why, I think deep learning has avoided the problem by just saying, I'm going to produce massive numbers, right? And then figure out what those numbers mean in the context of every language.
And definitely, I think that many people are still wondering, is that interlingual problem still a thing? So particularly in terms of media representation of some of these, we see it kind of reinstantiated. So we have one question that came in from the audience that asks some questions about the relationship between biometrics and sort of voice identification, voice recognition, et cetera, and the context of natural language processing. And the question is, I understand that speech recognition is different than identification or authentication a la biometrics. Now, with AI and ML applied to speech recognition, is there any technical overlap or any bleeding into these two areas?
I'll just say this, like, as I presented upfront, this methodology of machine learning, and that methodology of machine learning is actually just, to a large extent, universally applicable to essentially every prediction and classification problem you want. There's at the top level a little bit of a taxonomy that's perhaps useful, which is problems that are sequence to sequence problems versus problems that are sequence to single prediction problems versus problems that are small set of samples, fixed set of samples to a prediction problem. Okay. Having said that, at the top level, all of these techniques, so there is sort of at the underlying research level, advances in speech recognition often spur advances in machine translation and in natural language processing, and I'm sure in other areas like, that you were mentioning. So yeah, there is definite overlap, but it's really at that level that we've figured out how to do research that advances are portable across a broad set of applications.
Rain, would you like to take a stab at that one?
So, I mean, in the case, I work mostly with text, so I think the question is more applicable to spoken language. I think there's a little bit of an analogy in terms of as we are able to personalize systems that analyze or generate text more, there's adapting to the language of the person becomes something that is more possible and also raises interesting issues. None of the systems I work with do much of that personalization on the fly. But I think that there's going to be, a lot of the questions that were raised earlier with respect to privacy, GDPR, and so on are going to become more salient when we start personalizing our systems more.
Yeah, that's a great point there. Rob?
So with that, I would like to thank you both very, very much. And thank you also the audience for attending today. So thank you, Maureen. Thank you, Brian, for sharing your insights. A recap together with a link to the recording and the slides from today's session will be posted on our website, which is where you can find the materials from previous classes as well. And you can sign up for our email list to receive updates for future events. And with that, I think it's a wrap, and thank you very much and enjoy the rest of your day.
Yeah, thank you all for hosting this and for your time, listening to us talk about subjects we love to talk about.
Thank you very much.
Thank you.
Thanks. Take care.